I'm Seong-Mook Cho, co-PI of this project and also researcher of Professor Brian G. Thomas, this project PI. It's really my pleasure to be here to make a presentation regarding our achievement on blue waters. We have conducted summer multiphase modeling of defect formation mechanism and electromagnetic force effects in continuous state casting. Before starting the presentation, I would like to express our many thanks to supporters and our collaborator. First of all, we really appreciate Blue Water and the NCSA for giving us the great opportunity to conduct the various high-resolution simulations on Blue Water. And thank our collaborator at UIUC and the NCSA, especially to Dr. Said Khoury and Dr. Ahmed Tahar and NCSA. We also appreciate the NCS for academic partnership with the Fluent HPC license for supercomputer simulation and normal licenses for the workstation simulation too. And thank Continuous Casting Consortium at University of Illinois and the Continuous Casting Center at Colorado School of Mines. And finally, our two national science foundations. This slide shows our sum of publication acknowledging blue waters. We have published over 10 papers in the past year, and currently there are several papers under review and in preparation. Now I would like to move on talking about our research. Steel is one of the most widely used material in the world for automobile, ship, and construction industries. Production is almost 2,000 million tons per year, and over 96% of this huge amount is manufactured from the continuous steel casting. So even small improvement on this process has huge impact on the industry. In the continuous casting process, molten steel flows from the ladle through the turn dish into the mold. It should be protected from exposure to the air by a slag cover over each vessel and by ceramic nozzle between the vessels. Also in the mold, the molten steel freeze against the water-cooled mold plate wall to form a solidifying steel shell. This shell contains the liquid fraction as the shell is withdrawn continuously from the mold bottom region. And in the mold region, there are complex multiphysics phenomena, and if these phenomena, if this phenomena are not controlled properly, they can cause the many defect formations such as the gas bubble defect, non-metal inclusion defect, the depression, and the crack formations. Next slide, we show the more details about the defect formation phenomena. The center schematic view show the various phenomena in a casting mode. These phenomena should be understood and controlled correctly to reduce the defect formations. Instability at liquid mold flux and the molten steel interface near the meniscus can entrain or entrap the liquid mold flux, which can result in the surface or internal defect on the final steel products. Also, argon gas are injected into the molten steel pool to prevent the nozzle clogging, but optimized casting condition can make the bubbles and the inclusion interrupted by solidifying steel shell. Another problem, initial solidification defect, may be caused by the non-uniform superheat distributions near the solidifying steel shell. And there are depression and the cracks caused by the undesirable thermomechanical behavior of the solidifying institution. But all these defects can be reduced if electromagnetic systems are correctly applied to this system. Next slide will show some details of these electromagnetic systems. Okay, as you know, steel is a conducting material, so applying magnetic field induces the current in the molten steel, and interaction between the magnetic field and induced current finally generate the Lorentz force in the molten steel. So to reduce the defects explained in previous slide, several electromagnetic systems have been being used to reduce the defects. And to control the flow pattern, surface instability, and the superheat transport, and the initial solidification, and the particle transport, and the capture, and the grain structure, and the internal quality, and the steel composition and distributions. So we will show the sum of our result here for double EMBR static magnetic field and the mode electromagnetic steering moving field effect on the multiphysics phenomena. In our research field, computational modeling is an essential tool because other experiments and the other experiments using the lab scale model and the real plant measurement are extremely limited due to the harsh environment and the huge size of the domain and the many process parameters which should be considered for this study. Traditional tool water model experiments is not affected by magnetic field. And molten metal alloy experiment using the X-ray system required us to make the small and the different geometry. And for real plant measurement, we can only look at the surface flow and the surface defect. So this is not helpful to fully understand the phenomena in between. So computational modeling is very important for our research field. Even for computational simulations, there are other difficulties. As explained, this process has various phenomena and they are strongly interrelated. So many coupled governing equations should be solved, and the process has the huge domain size, and the defect have the micrometer length scale, and the defect formation time is only millisecond. So there are many difficulties explained. The process condition should consider many governing equations, and the processor has the huge domain size, and the defect size is very small, and we should consider the very small time step size. So this simulation is the very computationally intensive. And to optimize this process and suggest some new design, there should be many parametric study using the model. So we use the blue waters by implementing the ANSYS front HPC simulations and multi-GPU based in-house code CUFlow for including the turbulence model, LES, and the standard capstone model, and SST K omega model, and the secondary phase model, including the VOF, and the DPM model, and the EE model, and the new hybrid multiphase model, EE-DPM, and the particle capture model, and the heat transfer model, and the magnetic hydrodynamics models. We have tested both CPU version and the GPU version of the in-house code CUFlow developed by our collaborator, Professor Banka, and the co-workers and University of Illinois. CUFlow has been developed to solve the governing equation for the three-dimensional transient multiphase flow and the particle transport and capture, employing the LES, VOF, DPM, and the particle capture model and the MHD models. Multi-GPU-based CU flow was recently implemented into the Blue Water XK node, and we achieved greater performance. Multi-GPU CU flow test on the Blue Water XK node showed a good speed up, 40 times faster compared to the workstation simulation, and this enabled us to have the less than 2 days for 30 seconds LES simulation of the MHD flow in a cluster domain with 14 million cells. So it's the huge benefit to use the Blue Waters. And we also tested the ANSYS front on Blue Waters XE nodes. We tested the LES coupled with the VOF model, and that model showed over 3,000 times faster compared to the workstation simulations. So this speed of breakthrough enabled us to consider the much finer domain and the smaller time scale. And we can also calculate the many cases at the same time. This is very important for the parametric study to figure out the practical strategy to improve this process and to find some solution to reduce the defects. Using both the CU flow and the front on Blue Waters, we developed the high-resolution model of the defect formation mechanism and electromagnetic force effect in continuous state casting. From the model simulation, we can get deeper insight into the defect formation mechanism and provide the practical strategy of the electromagnetic system operation to reduce the defect. Today, I'm going to talk about some of our research projects using the Blue Waters as follows. Top surface interface variation effect on the slag entrainment defect using the LES coupled with VOF, and bubble behavior and the size distribution using the new hybrid multiphase model, EEDPM, and the argon bubble transport and the capture with the electromagnetic braking effect using the LES coupled with the DPM particle capture model and the electric potential MHD model, and the initial solidification defect formation modeling using the capsule model and the heat transport model. And we also investigate the effect of the electromagnetic steering effect on the initial solidification defect using the magnetic induction MHD model. And finally, we simulate the depression and the crack formation using the multiphysics modeling, which coupled the thermal turbulent model with the thermal mechanical behavior model. This slide shows how our developed model are used and how they are strongly related. For example, bubble size distribution from the EEDPM model is used as the input data for the particle capture model simulations. And then MHD model is coupled with this particle capture model, so we can investigate the effect of the electromagnetic braking on the particle transport and the capture. Another way initial solidification defect can be studied considering electromagnetic moving field effect by coupling the thermal turbulent model with the MHD model. Let me show some of our modeling results. This slide shows our LES coupled with the VOF simulation to quantify the transient liquid slag and the molten state interface and slag entrainment defect formation. Jet flow from the nozzle is wobbling, showing the up and down motion in casting directions. And this causes the instability at liquid mold flux and the molten state interface. Sometimes this instability is so severe that the liquid mold flux is interrupted by the solidifying station, resulting in the critical defect on the final state product as shown in the right bottom photos. We used the new hybrid multiphase model, EEDPM, to simulate the bubble behavior, including the bubble pocket formation, shearing up, volumetric expansion, and the breakup, accumulation, and the coalescence. The model can calculate the bubble size distribution change more accurately, considering all these phenomena. The model was validated with the water model experiments. Also, this EEDPM model was also validated with the low melting temperature alloy experiments showing the gas pocket locations and size distributions. And then the validated the model was extrapolated to calculate the real argon bubble behavior and the size distribution in the molten steel in a real cast nozzle. Next one, we simulated the transport and capture of the bubbles as steel shell front using the LES coupled with the DPM particle capture model and MHD model. From this model simulation, we can consider the effect of the EMBR on the bubble capture defect formation. The model was validated by the comparing with the plant measurement of the real defects in the steel plant. We found that with the EMBR, less bubble reach the solidifying steel shell, and the less bubble go deep into the more deep region, as shown in the left two figures. So EMBR increased the more flotation and reduced the bubble capture into the steel shell. This means that less surface or internal defects with the EMBR effect. We also investigate the initial solidification defects such as the meniscus freezing and the hook formation and the longitudinal crack formation near the meniscus using the RANS-based capsular model coupled with the heat transfer model. We found that distribution of the superheat flux around the mold parameter can be very non-uniform due to the unoptimized mold flow pattern. In particular, superheat is unable to reach the meniscus corner region. This can lead to the deep hooks and the longitudinal crack formations. In addition to this research, we investigate the effect of the mold EMS on the mold flow pattern, temperature distribution, and the heat flux, superheat distribution using the magnetic induction MHD model. And the mold EMS has a strong phase shift, and that field creates the rotating field around the perimeter of the mold wall, as shown in the videos. So high Lorentz force around the mold wall rotate the flow near the shell front, and these steering actions make the temperature and the superheat flux more uniform at the meniscus region, including the corner regions. You can see this effect by comparing the dashed lines around the shell front with the solid lines. This effect is expected to reduce the initial solidification defect so long as the magnetic field strength is within the optimum range which model is being used to predict. Finally, we used the calculated superheat flux profile at the shell front as an input data for the modeling of thermomechanical behavior of the solidifying steel shell. The thermomechanical model considers the phase transformation during the steel continuous casting. And from this model simulation, we can quantify the very important mechanism of the depression and the crack formation on the steel slab surfaces. Let me summarize my talk. So we achieved the speed up breakthrough on the blue waters for the high resolution simulations for the continuous steel casting. ANSYS Frontier HPC showed 3,000 times faster, and the multi-GPU based in-house CU flow showed 40 times faster on the XK node. And with these blue water resources, we conducted the various multiphase simulation of the defect formations and the electromagnetic effects for the continuous steel casting. Thank you so much for your listening.